In 5.2, we are going to be graphing rational functions by hand. We're not going to be using transformations because our rational functions can get very complicated. Remember, it's just a polynomial over another polynomial. So we're kind of going to be moving away from the 1 over x and the 1 over x squared. The key thing to graphing our rational functions is going to be to find the asymptotes if they exist, and you want them to exist because that helps you. Remember what your asymptotes are. They're guides for you. Your graphs will follow the asymptotes. So if you have asymptotes, you don't have to find as many points. In your book, there is a definition of what vertical and horizontal asymptotes are. This notation may be a little bit difficult to understand, so I'm going to break it down a little bit and then look at the graph below to illustrate what this notation means. So let's say you have your rational function f of x, and it's just some polynomial p over another polynomial q. Well, if f of x, if you look at its absolute value and it approaches positive infinity as x gets closer and closer to some number a, then the line x equals to a is going to be a vertical asymptote. And if f of x gets close or approaches some number b as the absolute value of x approaches infinity, then the line y equal to b is a horizontal asymptote. So the reason why that definition is a bit confusing is because we are using function notation and we have absolute values. So let's first change it. Absolute value of f of x, that's just the absolute value of y. And if absolute value of y is going towards infinity, we could also write that as if y goes to infinity or y goes to negative infinity. Remember, absolute value, you've got the positive and the negative. As the x value approaches some number, then x equal to a is a vertical asymptote. Let's go down to this graph, and then I'll show you what I mean by all this notation. Okay, so if y goes to positive infinity, that means your graph is going up. If y goes to negative infinity, your graph is going down. So we're going to look and see what happens as we approach some a value, which would be our vertical asymptote. Why don't we look at x equal to negative 2? So in that definition, negative 2 would be the a value. And it's saying, okay, look at what happens as you approach negative 2. What's happening to your y values? What's happening to the graph? Well, if the graph goes up forever or down forever, it's a vertical asymptote. Let's go ahead and approach our negative 2. We can come in from the left or the right. So let's come in from the left. As my x values get closer and closer and closer and closer to negative 2, notice that my graph is going down, down, down forever to negative infinity. So we approach negative 2, y went to negative infinity. That's a vertical asymptote. I don't even have to check the other side, but I will. Let's say we're coming in from the right of negative 2. Now remember, we're ignoring all the rest of the graph. We're just looking at points close to negative 2. So if your x values are getting closer and closer and closer to negative 2 from the right, for those x values, the graph is going up forever to positive infinity. So as we approach negative 2, our y values on one side went to negative infinity, the other side went to positive infinity. So yes, it is a vertical asymptote. And we can do the same thing for x is equal to positive 1. Let's go on to what a horizontal asymptote is. So if y approaches some number, as x goes to negative or positive or negative infinity, then y equal to b is going to be a horizontal asymptote. So this is saying it's talking about end behavior. So remember, horizontal asymptotes, that would be end behavior. And I know it's end behavior because when I'm looking at my x values, they're going to positive infinity and negative infinity. So that's just the ends of the graph, right? Where x is getting really, really large or really, really small. So if the y value approaches some number when x gets really large or really small, then that would be the horizontal asymptote. Let's go ahead and go back to our graph and look at our horizontal asymptote. In this case, it would be our y value equal to negative 2. That would be the b value in the definition. So think about what that's saying. It's saying, and let's look at how x goes to positive infinity. So if you go to the very far right of the x-axis and you look at all these x values, as they get larger and larger and larger, approaching positive infinity, notice that the graph is approaching my horizontal asymptote, which is y equal to -2. And then go to the left-hand side. As the x's go towards negative infinity, we see that the graph here is approaching y equal to -2. So again, that's just behavior at the ends. Now, just to emphasize, a rational function will never touch or cross vertical asymptotes because that's where the denominator is 0, so the function is undefined. However, as far as horizontal asymptotes go, it is possible for your graph to either cross over or just to touch a horizontal asymptote, or in fact, any other asymptote that is not a vertical asymptote, because those the horizontal asymptote, and as we'll see, other asymptotes as well, that's describing the behavior at the ends of the graph. In the middle, it can do all sorts of funny stuff. Let's go back and look at these boxes here. So we've described what it means to be an asymptote using math symbols. Now let's find our vertical asymptotes and our horizontal asymptotes. Looking in these boxes, if we were to find our vertical asymptote, the first thing we want to do is factor, if possible, our function. And then we're going to note the domain. So we're going to write down the domain. It could happen, because remember, these are fractions. Once factored, maybe we can cancel some common factors on the top and the bottom and reduce. So reduce the function if possible. Once it's reduced, then we're going to find our vertical asymptotes by setting the denominator equal to 0 and solving for x. Let's pause and let's look back at this graph. The equation for it is f of x equal to -2x squared plus 5 over x squared plus x minus 2. Let's say I was going to find my vertical asymptotes. Well, the first thing I want to do is I want to, if possible, factor this and find the domain. So it's going to be f of x, you know what? I like y, equal to -2x squared plus 5. The denominator does factor. It's going to be x plus 2, x minus 1. So I've factored it, and why I wanted to factor it is because it's easier for me to see what the domain is. Remember, you're looking at the restrictions, what makes the denominator equal to 0. So if x is equal to -2, or x is equal to 1, the denominator will be 0. So x cannot be -2, x cannot be 1. And I'm going to write down the domain. The domain is going to be everything except -2, so negative infinity to -2. So remember, when you write down in interval notation, you're going from small to large. Union, we could pick anything from -2 to 1. Union 1 to infinity. So that's my domain. Now let's find our vertical asymptote. First, can we reduce? And the answer is no. F of x is already reduced. 3, vertical asymptote. That's where the denominator is equal to 0. This is already factored. So when you find your vertical asymptotes, and I'm going to use VA for vertical asymptotes, all you have to do is set x plus 2 equal to 0 and x minus 1 equal to 0. To get x is equal to -2, x is equal to 1. Remember, the vertical asymptote is not the number -2 and it's not the number 1. These are vertical lines, so they have to be written as x equal to -2, that's one line, and x equal to 1, that's another line. All right, so we found our vertical asymptotes. Let's go back up and look at finding horizontal asymptotes in that next box. So when we're finding horizontal asymptotes, what we're going to do is divide the reduced function, if it can be reduced, so that would be factor and cancel, by the variable of greatest degree. And then we'll evaluate as x goes to positive and negative infinity. All right, first thing we want to do when we look at our, I like blue better. When we look at our horizontal asymptotes, 1. Divide by the variable of greatest degree. Okay, I'm going to use y instead of f of x. So it was y equal to 2, negative, I got to remember that negative, 2x squared plus 5 over x squared, and I'm not going to use the factored form, plus x minus 2. This was our function. The variable of highest degree is x squared, because the square, the exponent 2, is the highest exponent. So what I need to do is I need to take this and I need to divide. Well, maybe I'll put it down here. The negative is still there. I need to divide all the terms by x squared. So it's going to be 2x squared over x squared plus 5 over x squared. You're dividing every term by the variable of highest degree. Denominator is going to be x squared over x squared plus x over x squared minus 2 over x squared. And we do this idea of dividing out by the highest degree. We use that a lot in calculus. If I were to simplify each one of these fractions in the numerator, and there is a negative here, I would get 2 plus the 5 over x squared is going to stay, divided by 1 plus 1 over x minus 2 over x squared. And the second part says evaluate for x going to positive infinity or negative infinity. Before I do that, I want you to think about something, and I'll do this off to the side. If you had a fraction where the denominator got bigger and bigger and bigger, but the numerator, the top, stayed the same, remained constant. Let's just say I had 1 over 1. And let's say I was to increase my denominator, say 1 over 10. And then still increase the denominator, numerator is staying the same, 1 over 100. And then 1 over 1,000. So think about what's happening to that fraction as a whole. We have 1, 0.1, 0.001, 0.0001. I might be messing up my zeros, but hopefully you could see that as the denominator grows, the fraction is getting closer and closer to 0. Again, this concept here comes up a lot in calculus. So let's go back to, and remember this is a y value. All we've done was take and divide each term by x squared, which we can do in a fraction, divide top and bottom by the same quantity. What's going to happen is that each one of these fractions where we have an x in the denominator, as x goes to infinity, these are getting closer and closer and closer to 0. So 1 over x, as x gets bigger and bigger, gets closer to 0. And it wouldn't matter if x is negative infinity or positive infinity. You would still be getting closer and closer to 0. So that's an abstract idea. Sometimes it's a little bit difficult for people to understand. So this is going to be a negative. We have that negative in front of the fraction bar. 2 plus 0. That's what it's getting close to. 1 plus 0 minus 0. Or negative 2 over 1, which would be negative 2. And then in our graph, you notice that that is our horizontal asymptote. It's y equal to negative 2. So again, all you have to do to find your horizontal asymptote is to take and divide by variable of greatest degree or highest exponent, either way. Again, we write the horizontal asymptote as y equal to -2. It's not the number -2. So those are the two ways that we find our asymptotes. Vertical asymptote, set denominator equal to 0 after you've reduced the function. And also for the horizontal, it would be after you reduce the function as well. In the next few examples, all we're going to do is find domain, vertical, and horizontal asymptotes. So I use VA for vertical asymptote, HA for horizontal asymptote to reduce the amount of writing because I'm lazy. So first of all, we always want to make sure that our function is factored. If you look at the 3x, can't do anything with that. X squared plus 1, can't factor it. I could factor it with complex numbers, but remember, we're graphing real numbers. X and Y are real numbers. So anytime you have a complex value, you can just ignore it. So x squared plus 1 will not factor with real numbers. So now our domain, we find by setting the denominator, or seeing what x values give us 0 in the denominator. Well, there are none. X squared plus 1, never going to be equal to 0. It doesn't matter if I put in negative numbers, positive numbers, 0. I always get a non-zero denominator. Now, what you could do is you could say, okay, well, why don't I just solve this equation for 0? And you would get x squared equal to -1, x equal to plus or minus square root of -1, which is complex. So the domain, since we can use any x value, it's going to go from -infinity to +infinity. And here what's really nice is once you have your domain, you know how many pieces to your graph you're going to find. In our previous example, the domain was in 3 pieces and my graph was in 3 pieces. Now here my domain is 1 interval, so I know my graph is going to be 1 piece. So we found the domain. Let's go ahead and find vertical asymptotes, but honestly, I've already found my vertical asymptotes. Remember how to find your vertical asymptotes is you set your denominator equal to 0, which we've already done. And we already found that the only solutions are complex, plus or minus I, which means there are no vertical asymptotes. And that's possible. Asymptotes are not, they don't always exist. Okay, what about horizontal? If I look at my horizontal asymptote, remember what we're doing is and here I'm going to replace f of x with y just because I like it. What we're doing is we're saying, okay, we're going to divide by the variable of highest exponent. In this case, it's x squared. So I'm going to have 3x over x squared divided by x squared over x squared plus 1 over x squared. And now when I reduce this, it's going to be 3 over x divided by 1 plus 1 over x squared. Now, as our x values go to positive infinity or negative infinity, doesn't really matter, numerator is going to go to 0, and the 1 over x squared in the denominator will go to 0, which means this is going to be equal to 0 over 1. 0 over 1 is just 0, which means our horizontal asymptote is the horizontal line y equal to 0. And you can always check this graph, 3x over x squared plus 1, in your graphing calculator or graphing utility such as Desmos. So we're going to find the domain in example 2. First thing I want to do is factor and see if anything cancels. This is going to be x plus 1 in the numerator, x plus 1, x minus 1 in the denominator. So this is going to reduce. However, key point, you must state your domain before you reduce. So our domain, we're looking at the denominator, and I note that x cannot be equal to -1, x cannot be equal to 1, or else my function will have 0 in the denominator. Domain's going to be negative infinity to negative 1, union negative 1 to positive 1, union 1 to, 1 to infinity. Found my domain. Now for my vertical asymptote, we're going to reduce, so I can cancel the x plus 1 in the numerator and denominator to get 1 over x minus 1. For the remainder of the values, we're going to use the 1 over x minus 1. Vertical asymptote, we set the denominator equal to 0. X minus 1 equal to 0 gives me x equal to 1. So the only vertical asymptote I have is x equal to 1. However, look at my domain. It's in 3 pieces. I'm supposed to have 3 pieces to my graph, and typically the graph will break up into pieces at a vertical asymptote, but I only have 1 vertical asymptote. And that is because when we reduced, we lost the x equal to negative 1. We canceled that out. But if you put in negative 1 into the original function, we'll still get 0 in the denominator. We still can't put in that negative 1. So what that means is that we have a vertical asymptote at x is equal to 1. The function is still not defined at x equal to negative 1, but at x equal to negative 1, there's a hole in the graph. So it's not an asymptote, it's a hole. So at negative 1, if we were to look at a graph, and you can throw this in decimals, you would have a hole. And then at 1, you would have a vertical asymptote. So that hole will make the function discontinuous at negative 1. So we're still going to have 3 pieces to our graph, but between 2 of those pieces will be a hole. Between the other 2 pieces will be a vertical asymptote. Okay, so there's a lot you can tell when you're finding domain, vertical asymptote, and horizontal asymptote. Let's go ahead and find our horizontal asymptote. When we find our horizontal asymptote, we're going to be dividing everything by x squared. Maybe I can fit it down here. So this is going to be, what was my function? X plus 1. So we get y equal to x over x squared plus 1 over x squared over x squared over x squared minus 1 over x squared. And I could see that in the top, I would have 1 over x, which would go to 0, plus 1 over x squared, which would go to 0. In the bottom, it's going to be 1 minus 1 over x squared. So 0, 0, 0. We get 0 over 1, which would just be 0. Horizontal asymptote, y is equal to 0. So we found the domain, we found all the vertical asymptotes, and we've also found the horizontal asymptote. Now again, you could put this in Desmos, but what I'm going to do is just do a real quick sketch. If I were to be graphing this, again, this is just a sketch. Remember, we're going to have a vertical asymptote at x is equal to 1. So I'm going to use a dashed line so that it's not being confused with the actual graph of the function. And then we have a horizontal at the x-axis, which would be y is equal to 0. So this is the idea, actually, when you're graphing these rational functions. Find your asymptote. And then we also have a hole. We have a hole when x is equal to negative 1. So if we put x equal to negative 1 into our reduced function, we'll have 1 over negative 1 minus 1, which would be equal to negative 1/2. So there's going to be a hole at the point x is equal to -1, y is equal to -1/2. -1, let's see, 1. So -1/2, probably going to be close to here. So that would be an open circle. And now I know my graph has to follow the asymptotes. So basically, it's going to do this and that. And if you graph this in Desmos, you'll see that there's going to be an upper portion, like so. So really, this is in 3 pieces. We have one piece from x is -infinity to -2, and then we have a discontinuous point, so we have to lift up our pen. And the second piece, or -1, sorry, from -1 to +1, lift up our pen, draw our third piece from x is equal to +1 to infinity. All right, and that's kind of the idea when you graph these. To get more accurate, you just find some additional points. Let's move on to example 3. In example 3, does that factor? Yes. The denominator factors difference of squares, x plus 2, x minus 2. It doesn't look like anything's going to cancel though. But I do notice that x cannot be equal to -2, x cannot be equal to +2, or else I'll get 0 in my denominator. And again, that gives me my domain, which would be -infinity to -2, union -2 to +2, union 2 to +infinity. Now let's go ahead and find our vertical asymptotes by setting our denominator equal to 0. In a case where nothing reduces, pretty much once you found the domain, you found your vertical asymptotes because they'll be the same. Vertical asymptote will be x equal to -2 and x equal to 2. Again, if you're not sure, just your denominator is factored, just set each factor equal to 0 and solve separately. And you'll get x equal to -2, x equal to 2. Found our vertical asymptotes. Now we find our horizontal asymptotes. Maybe I'll just go right here. We're going to take our y equal to x to the third over x squared minus 4, divide everything by x to the third. So in the numerator, we're going to have x to the third over x to the third. Denominator is going to be x squared over x to the third minus 4 over x to the third. And then in the numerator, that's going to reduce to 1. Over denominator is going to be 1 over x minus 4 over x to the third. As the x's go to positive or negative infinity, these fractions in the denominator are going to go to 0. What we have here is 1 over 0, which does not exist, which means there are no horizontal asymptotes, and that can happen. Remember what the horizontal asymptotes tell us, though. That gives us our end behavior. Now, rational functions are nice, smooth functions. They may have some holes in them, but they're nice, smooth functions, and their ends go on forever. So if your ends are not approaching some horizontal asymptote, the only other choice is that they're either going to negative or positive infinity, and we'll look at that case as well. So as far as our vertical and horizontal asymptotes, in these 3 examples, we've seen examples where there is no vertical asymptote, but horizontal, examples where they're both, and example where there's a vertical but no horizontal. We looked at vertical and horizontal asymptotes, but there could actually be other asymptotes. And that's what we're going to do next. We're going to look at how we would find other asymptotes. Basically, what you're doing is you're looking at the degree of the numerator and the denominator. If the degree of the numerator is larger than the degree of the denominator, so that would be similar to what we had in our last example. Example 3, we had an x to the third, and then in denominator, it was x squared was the largest. So in the event that top larger than bottom, then do long division and ignore the remainder. So here's a note. If the degree on the top is larger than the degree on the bottom, there will not be a horizontal asymptote. However, there may be a different asymptote, such as what's below, which would be an oblique asymptote. An oblique asymptote is just a slanted line. So vertical line is vertical, right? Vertical asymptote, vertical line. Horizontal asymptote, horizontal line. So if you have a line that slants, not vertical, not horizontal, that would be an oblique asymptote. Sometimes we just call it a slant asymptote because it is a slanted line. That happens if the degree of the numerator is exactly one more than the degree of the denominator. So that would be an example of what we had in our last example 3, where the degree was exactly one more. So that would give us an oblique asymptote. And like in example 4 here, notice that we have an x to the third in the numerator, but an x squared in the denominator. So the x to the third is one more than the x squared. We will have an oblique asymptote. In the event that you have an oblique asymptote, you will not have a horizontal asymptote. So you either have one or the other. When you think about it, if you have a horizontal asymptote, that means as your x's go to either negative or positive infinity, your y values, your graph, is approaching some horizontal line. So if there's no horizontal asymptote, you're not approaching some horizontal line, you're not approaching some number, it must be true that the ends will go to either negative or positive infinity. And they will follow perhaps a slant or an oblique asymptote. So in example 4, we're going to find domain and then all asymptotes, not just horizontal. We do what we did previously. We look at our function and we see, well, can we factor and cancel? The 2x to the third in the numerator is factored. Denominator would be x plus 2, x minus 1. So that is factored, nothing cancels. However, for the domain, note that x cannot be equal to negative 2. X cannot be equal to positive 1. And right away I get domain, which again tells me how many pieces I'm going to have to my graph. Negative infinity to negative 2, I'm going to have one graph there. Union, negative 2 to 1, another piece of my graph. And then the last piece from 1 to positive infinity. Vertical asymptotes. There are no holes in this graph because nothing canceled. The only way you're going to get holes is if something cancels and your function reduces. But since it's not reduced, I'm going to have vertical asymptote, no holes. And the vertical asymptotes would be whatever makes denominator 0. So x equal to negative 2, x equal to positive 1. Again, you could set x plus 2 equal to 0, x minus 1 equal to 0 and solve. But I can just look at that and see what my vertical asymptotes will be. Horizontal, there's none. And I don't even have to do the work. I see that the degree on the top is larger than the bottom, so I'm not going to have a horizontal asymptote. But let's say you're on autopilot. Let's say you wanted to do that computation. Then you would just divide all the terms by x to the third to get 2x to the third over x to the third divided by x squared over x to the third plus x over x to the third minus 2 over x to the third. And then we have have 2 over 1 over x plus 1 over x squared minus 2 over x to the third. Notice that in the denominator, every single one of these fractions are going to go to 0 as x goes to either positive or negative infinity. So you're going to get 2 over 0, which does not exist. And that tells me I do not have a horizontal asymptote. However, I might have an oblique asymptote or maybe a different asymptote. I'm going to do the long division. Remember, this would be 2x to the third, top divided by bottom. Bottom is x squared plus x minus 2. It would be nice if that was a binomial, then I could do synthetic division, but it's not. And in fact, I'm going to have to put in some 0 placeholders for the x squared, the x, and the constant. Now when I divide by x squared plus x minus 2, what I'm looking at is what do I need to multiply the x squared by to get a 2x to the third? And that would be a 2x. If you need to do the multiplication off to the side and do the 2x times the divisor x squared plus x minus 2 to get 2x to the third plus 2x squared minus 4x, and then you can do that multiplication off to the side. We'll get 2x to the third plus 2x squared minus 4x, and then subtract down. When I subtract down, I get 0. I get a 0 minus a 2x squared, which would be a negative 2x squared, and then 0 minus a negative, or minus 0 minus a positive would give me a negative 2x squared. 0 minus a negative would give me a plus 4x. And then bring down the 0. I need to multiply the x squared by a negative 2, so minus 2 in the quotient. And I would get a negative 2x squared minus 2x plus 4. Again, you could do that multiplication off to the side if you need to. This would be 0. 4 minus 2 would be a 4 plus 2. This is a 6x. 0 minus 4 would give me a minus 4. So I did the long division. I can't go any further. I need to ignore the remainder and then just look at the quotient up here. So remember what this is. This is y values. This is y equal to 2x minus 2. That would be the line, the slanted line or oblique asymptote. So my oblique asymptote is y equal to 2x minus 2. So I did have an oblique asymptote. I did have a vertical, in fact I had 2 vertical asymptotes. I did not have a horizontal asymptote. And I found my domain, which tells me that I'm going to have 3 pieces to my graph. Although this is not part of the problem, let me go ahead and use Desmos to just sketch what this graph might look like. And this is not going to be to scale. So I had one vertical asymptote at x equal to negative 2. So I'm going to pretend like this is x equal to negative 2. And then I had another one at 1. I also had an oblique. So let's think, y equal to 2x minus 2. If x is 0, y is negative 2, so somewhere down here. If x is 1, y is 0, and I have my oblique or slant asymptote. Y equal to 2x minus 2. In Desmos, if you were to look at the graph, you would see that we have one piece to the right of x equal to 1, the vertical asymptote, and above the slant asymptote. You cannot have a piece above the slant and also below. Some people make that mistake. Remember, the vertical asymptotes will split your graph into pieces, and there can only be one piece to the right of x equal to 1. It's either going to be above the slant asymptote or it's going to be below the slant asymptote. And in this case, it's above. Now, if we look in the middle portion on, again, Desmos, what we're going to do is come down and then go up. So in between the x equal to -2 and the x equal to 1, we have another piece of our graph. Also notice that this graph is crossing over the slant or oblique asymptote. Remember what I said, graphs will never cross-touch vertical because that's where the denominator is undefined. However, it can touch or cross other asymptotes like a horizontal, or in this case, an oblique asymptote, because horizontal, oblique, that's just telling us how our graphs behave at the ends. So notice the end here. This graph will keep going up forever and ever and ever to positive infinity as your x get larger and larger and larger. In the middle, we've got this squiggly piece. And then if you go to the left of x is equal to -2, way at the bottom here, and again, you can look on Desmos, you're going to have another piece to the graph. So you can see that the end behavior here would be all the way down to -infinity. So those oblique or slant asymptotes, our graph will follow it at the ends, but notice not in the middle here. Now there is a shortcut when you're finding asymptotes besides vertical asymptotes. So this would be the box at the very bottom. This would be a shortcut for non-vertical asymptotes. So let's say that you have your function which is equal to p of x over q of x. And we're going to let m be the degree of p of x, and then a is going to be its leading coefficient. So going back to our function here, that would be 3 would be the degree of p. Our p is 2x to the third. 2 would be the leading coefficient. Now in the denominator, we have another polynomial q. Degree is 2, leading coefficient is 1. And that would be the b value here. So if you have a rational function, m is going to be the degree of the numerator, a leading coefficient, and then we're going to let n be the degree of the denominator, b is going to be leading coefficient. And we're going to look at these conditions. Let's just say that the degree on the top is smaller than the degree on the bottom. So that would be like our example 1 and 2. Then your horizontal asymptote will always be just y equal to 0. If the degrees are the same, then to find your horizontal asymptote, you would just look at those leading coefficients, and it's just the fraction of the leading coefficients. If top is bigger than bottom, but only by 1, then you have an oblique asymptote and you have to do the long division. So too bad. But steps 1 and 2 are shortcuts for finding horizontal asymptotes. Now we're going to finally put all of this together. When we're graphing our rational functions, and this order may differ from that in your book, first thing we want to do is find our domain. Again, that just tells us how many pieces we're going to be graphing. So to find your domain, you just set denominator equal to 0 and solve. If possible, reduce your function. And then find vertical asymptotes after you reduce. That will also give you holes if it reduces. So now we're just going to use the reduce function for 2 through 7. Part 3, find any horizontal or other asymptotes. Again, we're going to use the reduce function if it reduces. And then if you do have a horizontal or oblique asymptote, find any cross or touch, because it is possible that it could cross or touch. And how you do that is you take your asymptote and you set your function equal to the asymptote. So we'll go through an example so you'll understand what I mean by that. That's just finding asymptotes, holes, and any cross-touch points of your horizontal or oblique asymptotes. Now we're going to find some easy points, because it's always nice to have some extra points. Y-intercepts. Y-intercepts are super easy because you're just putting in 0 for x. And then x-intercepts, it's a fraction. Rational functions are fractions, so to find the x-intercept, you would set that fraction equal to 0 and solve. But since it is a fraction, the only way a fraction can equal 0 is if the numerator is 0. So all you have to do is set the numerator, that top polynomial, equal to 0. And again, we'll go through these examples. If you need to find additional points, and then the points that you want to find would be near vertical asymptotes, typically, or any cross or touch points. Let's put this all together in example 5. So we're going to sketch this graph, and we're going to include any asymptotes or holes if there are any. First, notice that this function is factored. Nothing cancels. I notice that in the denominator x plus 3, if x is equal to -3, denominator is going to be equal to 0, which gives me my domain. It would be everything except -3, -infinity to -3, and then -3 to +infinity. I am probably going to start graphing this. So that would be number 1, finding the domain. As I find things, so I know it's going to be 2 pieces. Step 2 would be vertical asymptotes. Nothing reduced, so I could see that my vertical asymptote, the only one I have, is going to be x equal to -3. Again, you're just taking x plus 3 equal to 0 and solving. I'm going to go ahead and maybe use red for that. Go to -3 and draw my vertical asymptote. So this would be x equal to -3. Maybe I'll make the tick points in blue because I like blue. Okay, horizontal asymptote. I could go ahead and divide everything by x, but remember we had that shortcut. The shortcut said if the degrees are the same, notice that this is 1 times x and 1 times x, the degree is the same, x to the 1, x to the 1, then all you have to do for your horizontal asymptote is take the leading coefficients, that fraction. So it's 1 over 1. But I'm going to not write it as 1 over 1. I'm going to write it as 1. So I do have a horizontal asymptote of y equal to 1. So it should be about here. Nice. Okay. So that would be 3. 4 said to find any points that may cross or touch the asymptotes from part 3. So we had a horizontal asymptote. Is it possible for my graph to either touch or cross that? Let's look at what that means. Our function f of x, and I'm going to use y, equal to x minus 4 over x plus 3. Okay, so I have this function, but I also have my horizontal asymptote, which would be y equal to 1. If my function is going to touch or cross the horizontal asymptote, that is where these two y values are the same. So all I have to do to figure that out is set them equal to each other. X minus 4 over x plus 3 equal to 1. And I'm going to write 1 as 1 over 1 as a fraction, because now I can use cross products. I can do x minus 4 times 1, which is simply x minus 4, equal to x plus 3 times 1, which is simply x plus 3. And now I could add 4 to both sides, And then notice if I subtract x from both sides, I get 0 equal to 7. That can't happen. There's no solution to this equation, which means there are no cross touch points. And in this case of our horizontal asymptote, which is good news, because now I know that my graph, when I do graph it, it's not going to cross over or touch my horizontal asymptote. It'll strictly follow. And you'll see what I mean when we get some points together. The next step, which would be 5, is to find some points for our graph so we can start sketching it. Number 5, maybe I'll do this down here. That would be the y-intercept. That's always the easiest point to find because notice that all you're doing is putting in 0 for x. So it's going to be 0, comma something. If you put in 0 for x, again, this is y, then you'll get -4 over +3 or -4/3. Maybe I'll write this as 0, comma, -1 1/3 because I'm going to have to graph it. Why don't I graph it now? So that says when x is equal to 0, y is equal to, we'll go 1, 2, -1 1/3, probably closer to the -1. Okay, let's go ahead now and find some x-intercepts. To find your x-intercepts, and this is true of any function, you just set your function equal to 0. And I'm going to do that, but then I'll show you the shortcut. The shortcut is just setting the numerator equal to 0. So if we were to set x minus 4 over x plus 3 equal to 0, right? Because it's where the y value is 0. Notice that this is like 0 over 1. Then when I do my cross multiplication, I'm going to have x minus 4 times 1, which would be x minus 4, equal to x plus 3 times 0 is just 0, which is the same as just setting that numerator, x minus 4, equal to 0. And I get x is equal to 4. So I have an x-intercept when x is equal to 4. So at x equal to 4, y is equal to 0 because it's an x-intercept. Let's go back to the graph. And we'll go 1, 2, 3, 4. 7 says find additional points if you need it. Well, if I look at the vertical asymptote x equal to -3 and I look at the right-hand side, I'm actually done. I can sketch the graph. Because I know that there's no cross-touch of my horizontal asymptote, I know my graph will have to follow it underneath. And I know my graph always follows the vertical asymptote, so I'll just make a smooth graph. You can get more points if you want, but remember, we're just sketching. It's always nice to label these points as well. So I know this is the point 4, 0. And then this was 0, -4/3. I have 2 pieces to my graph. I'm going to have another piece to the left of x equal to -3. And I already know that it has to be above the horizontal asymptote. And the reason why is, think about it this way, and I'm going to get rid of this once I draw it. I'll do it in a light color like yellow. Let's just say the graph was below and it followed the asymptotes. Notice that eventually it's going to have to cross over the x-axis, but that would mean I would have another x-intercept, and I don't. So I already know that the only possibility for this graph is that it's above the horizontal y equal to 1. I just don't know where it is. So maybe in this case for part 7, I should find additional points. A good point would be, so this would be -3, so maybe a -4. Putting in an x value of -4. That would give me a y value of -4 minus 4 over -4 plus 3, or -8 over -1. It gives me a +8. That would be the point -4, comma 8. And that makes sense to me. I should have and 8 is probably way up here. We'll just pretend like that's 8. I should have a positive value above y equal to 1. So that does make sense to me. And I'm going to go ahead and label that -4, 8. So that's it. A lot of steps. It is tedious, but the steps should all make sense. Again, don't forget that you can always check all of these on your graphing calculator or Desmos. Example 6, we're going to sketch a graph, include any asymptote or holes. First thing we want to do is get domain by factoring. And here the denominator, difference of squares, would be a +2 and a -2. So I can see that this will reduce. The x plus 2 in the numerator and denominator will reduce. But I want to write my domain down before I reduce. My domain, that would be that x cannot be equal to -2, x cannot be equal to +2. Again, once I reduce, I'm going to lose that x is equal to -2, and that will become a whole, which means this will go from -infinity to -2. That'll be one piece. Another piece from -2 to +2. And then I'll have another piece to my graph from 2 to infinity. Now that I've found my domain, I can go ahead and reduce the x plus 2 to have 1 over x minus 2. And this is what I'm going to use for the remainder of the information that I need to find. In part 2, we want to find vertical asymptotes. If I set x minus 2 equal to 0, I get x is equal to 2. However, remember that in my domain, I had 2 points. I had a -2 and I had a +2 where the function was undefined. So the x equal to 2, since that's a vertical asymptote, that takes care of that break in my graph. So that must mean that I'm going to have a hole when x is equal to -2. So to figure out that point, I'm going to put -2 into the reduced function 1 over x minus 2, which would give me a y value of 1 over -2 minus 2, or -1/4. So we're going to have a hole at the point -2, -1/4. I'm going to go ahead and start graphing. X equal to 2, that'll be one of my vertical, well, actually my only vertical asymptote. And then at this point, -2. So maybe this would be a -2. And then -1/4 is really small, kind of close to that axis. So I'll just put a hole there for now. And then I'm going to continue on. So let's go to 3 and find any horizontal or oblique asymptotes. I notice that the degree in the numerator is less than the degree in the denominator, so right away I get that my horizontal asymptote is y equal to 0. Again, if you don't see that, you can just divide top and bottom, all the terms, by x squared, and you'll get 0 in the end. So I'm going to put right above my x-axis, I'm going to sketch my horizontal axis, and I'm doing this because I want to remind myself that my graph has to follow this. Okay, so I have my asymptotes, I have a hole. Now I want to figure out if there's any cross or touch of this horizontal asymptote. That would be part 4. So again, remember this function, again, I'm using the reduced function y equal to 1 over x minus 2. And my horizontal asymptote was y equal to 0. If there's going to be a touch or cross, it's going to be where these guys are the same. So I just set them equal to each other. 1 over x minus 2 equal to 0, or 0 over 1, so you can do your cross products. We have 1 times 1 is 1, equal to x minus 2 times 0 is 0. And since 1 is not equal to 0, that means there's no cross-touch. And I'm happy, because that makes everything nice. I know that my function will exactly follow my asymptote, my horizontal asymptote. Let's look at number 5. Number 5, we're finding our easy points, such as the y-intercept. To find your y-intercept, put in 0 for x. If you put in 0 for x, you'll get 2 over negative 4, or negative 1/2, for your y value. So if I go to 0, negative 1/2, that's a point on my graph. And then 6, x-intercepts. To find your x-intercepts, you set your numerator equal to 0. Again, remember, we're using the 1 over x minus 2. So if we're using 1 over x minus 2, the numerator can never be 0. So there is none. Again, if you want to, go ahead and set the whole expression equal to 0 and solve. You will get 1 equal to 0, which cannot happen. No x-intercept. All right, so I am not going to find additional points yet. I'm going to see where I am on my graph. The left-hand side of the vertical asymptote, x is equal to 2, I'm actually done. I know that my graph has to follow the vertical asymptote and follow the horizontal asymptote. I do have a hole, so I have to sort of pick up my pen and keep going. So that's 2 pieces, right? I have 1 piece from negative infinity to this point negative 2 for that x value negative 2. And then maybe I'll go ahead and label that hole just so we remember that this is negative 2, negative 2, negative 1/4. And then we have 0, negative 1/2 for our y-intercept. And that's all I need on that side. Should I use 3 or 4? I need another point on the other side of the vertical asymptote, x is equal to 2. So that would be number 7, additional points. Because I don't know if the graph is going to be above the horizontal asymptote y is equal to 0 or below. If I put in 3 for x, I get a y value equal to 1 over 3 minus 2. That would be 1. Again, I'm using the 1 over x minus 2, the simplified or reduced version. So 3, 1, and I'm done. My graph has to follow my asymptotes. So I'll just go ahead and label this 3, 1. So you see this is long, it is tedious, but all these steps should make sense. Factor, if possible. Find your domain by setting denominator equal to 0. Find your vertical asymptote. If your function reduced, then you will also have some holes. And then you set reduced 1 to find vertical asymptote, horizontal asymptote, or oblique, and all the remaining points. Let's look at the last example we're going to do for this section, and we could keep going. There's so many different variations of rational functions, but then this is just going to get crazy long. Example 7, sketch the graph, include any asymptotes or holes. So again, first thing I want to do is factor, find my domain. Numerator does not factor. Denominator would be x plus 5, x minus 1. So it does factor, but it does not reduce. Notice that x cannot be equal to negative 5, x cannot be equal to 1, or else my function will be undefined. And again, that gives me my domain. That gives me the domain negative infinity to negative 5, negative 5 to positive 1, 1 to infinity, 3 pieces in my graph. Vertical asymptote. Nothing reduced, so I could see just by looking at that denominator that x equal to negative 5 and x equal to positive 1 would be my vertical asymptote. I have no holes. No holes because nothing reduced. I am going to go ahead and pretend like this is a negative 5. Again, this is not to scale. And a little bit closer to the y-axis would be my x equal to 1. 3 pieces, 1 piece to the right of 1, 1 piece between the negative 5 and the 1, 1 piece to the left of negative 5. 3. Looking at the degrees, degree in the numerator, less than degree in the denominator. My horizontal asymptote is y equal to 0. Again, if you want to go ahead and divide out by the x squared, you will still get y is equal to 0, but I'm going to use that shortcut. And I am just drawing my horizontal asymptote right above my x-axis to remind myself that this is what my function will follow. So let's see if we have any cross or touch of our horizontal asymptote. We are setting, nothing canceled, too bad. We are setting x over x squared plus 4x minus 5. We're setting that equal to our horizontal asymptote of 0. So 0 over 1. When I do the cross products, I get x times 1 is x. X squared plus 4x minus 5 times 0 is 0. So actually x is equal to 0 is going to be a point where it's going to touch or cross. So I need the x and the y value. I already know the y value. It's the horizontal axis, which is y equal to 0. Or you could just put that x is equal to 0 back in the function to get y is equal to 0. So the point 0, 0, this is going to be a cross or a touch of that horizontal asymptote. So look at this. You can see at that point I am on the horizontal asymptote. Let's go ahead and find our y-intercept, and I already know what the y-intercept is because I can see it. I already graphed 0, 0. That's the y-intercept. Remember, to find your y-intercept, you let x be 0, which we already did. If you put x is equal to 0 in your function, you get y is equal to 0. So I already know that I have my y-intercept, and I also know that that's an x-intercept as well. But remember, we can have more than one x-intercept. We can have more than one 0. So if I were to find my x-intercept, I would be setting that numerator, x, equal to 0. You can set the whole function equal to 0, but you will still, the denominator will still go away because you'll be multiplying it by 0. And that gives me the point 0, 0, which I knew it would. The point of actually finding the x-intercept is there might be more than one x-intercept, but what I see here is I just have that one x-intercept. Let's go back to our graph. So far I have some asymptotes, but I only have one point. I'm going to need a lot more information. If I look to the right of the vertical asymptote x equal to 1, maybe I'll look at 2. My graph will either be above y equal to 0 or below y equal to 0. So that would be a good idea for an additional point. And we're going to have a lot of additional points this time. X equal to 2. That will give me a y value equal to 2 over 4 plus 8. You can put this in a calculator, minus 5. And I get 2 over 7. That would be the point 2 comma 2 over 7. So 2 over 7 is pretty small, but it's positive. So I know it's going to be above the horizontal asymptote, close to the x-axis. And I actually only need 1 point. I already know that my graph is not going to touch or cross horizontal. It will never touch or cross vertical. So it has no choice. It has to follow the asymptotes. And maybe I'll just go ahead and label this point 2 comma 2 over 7. I'm going to ignore the middle portion for now and look at the left of vertical asymptote x equal to -5. And maybe I will pick -6. If x is equal to -6, then y is going to be equal to -6 over 36 minus 24 minus 5. That'll be -6 over 7. So really close to -1. I'm going to be graphing the point -6 comma -6 over 7. Okay, but my y value is negative, so I know it's going to be below the horizontal asymptote. Maybe I should erase this -6. It's kind of in the way. Okay, it'll be close to the -1. And now I'm done on that side. No choice, it has to follow the asymptotes. And I'll go ahead and label that point as well. -6, -6 over 7. All right, let's look at the middle. Middle is going to be challenging because I do have a cross touch point. So when you have a cross touch point, what you have to do is you have to get some values on either side of that point to see if the graph will be above our horizontal asymptote y is equal to 0 or below. So it's possible, and I'm going to sketch this in yellow, it's actually not part of the graph. It's possible that we could start out really high and it'll look kind of like a parabola, just touch. Or it could go low, come up, just touch. Or we could start high. Let me get rid of this stuff. We could start high and then, hey, how come I can't erase? I lied. Okay, we could start high and then pass through our cross touch and go low. Or we could start low, cross through and go high. There's actually 4 choices here. So what we need to do is just to find values on either side of that cross touch so we can get a better idea of what our graph looks like. So maybe a good point to try would be, let's see, this was -5, right? Where this other vertical asymptote was. So we have x values between -5 and 0. Maybe we could choose a -1 or a -2. Maybe I'll do a -2. Kind of more in between the -5 and the 0. So if x is equal to -2, I'm going to have a y value of -2 over 4 minus 8 minus 5, which would give me -2 over 11. I think, double check me on that. Is that -2 over 11 or +2 over 11? Ooh, no, it's negative over negative, which would give me a positive. Ooh, so bad. Okay, double check. Negative, yes. So -2, it's going to be a +2 over 11. So that's going to be really, it's positive, but it's really close to the x-axis. However, that tells me that my graph is going to go up. It has no choice. It can't come back down because then it will cross back over the x-axis and I would have another x-intercept, which I don't have. I found all my x-intercepts. So now the question is, between x equal to 0 and x equal to 1, is it going to go back up or is it going to come down? I have to find a value in between, and it looks like x is equal to 1/2 might be the best choice. which would give me a y value of 1 over 2, let's see, 1 over 4. This is going to be a plus 2. Let's see. And then a minus 5. Fractions always kind of get me a little squirrely. If I put that in a calculator and then hit my fraction decimal key, I get negative 2 over 11. So I cheated. X was 1/2, y was negative 2 over 11. All right, that tells me that when x is equal to 1/2, the y value is going to be negative, but really close to that x-axis. But that also tells me the direction. It's going to go down. Definitely double check by putting this in a graphing utility. The more vertical asymptotes you have, the more difficult it is to graph these rational functions. But anyway, we'll stop here, and that's it.